Let's continue now with week 5 talking about quantum mechanics. Now that's a pretty scary term, but for the purposes of this class, we're going to take a pretty simple approach to this. Things that I'm going to talk about at this point are illustrations or models that show the structure of atoms. And this is a scientific guess. It's a bet that is based on the data as we know it. When we do this, we talk about models, and a model is an idealized, almost cartoon-like structure that helps us to understand how we think things are actually functioning and how things are put together. So quantum theory states that electrons do not absorb or release energy in a smooth, continuous fashion, but they release energy in packets known as quanta. If you can think about two ways of entering a building, one way you enter the building is to go up the ramp that the wheelchair rolls up. That's a smooth approach to moving up a hill or increasing your potential energy, if you remember that term from previous discussions at home or other science classes. On the other hand, if you go up the stairs, which is the other choice, these are discrete packets of movement that would be representative quanta of movement. So each step that you take up is a quantum or a packet of energy that you expend in order to go up into the building. So you can either go up the ramp, which is a continuous smooth flow, or you can go up the stairs, which are these quantized flows. And what the quantum theory says is that electrons either absorb or release energy in packets as opposed to a smooth flow of energy. The Bohr model is a model that was written by Niels Bohr, and it states that the nucleus is surrounded by orbits, as we've said before, but that each of these orbits is a specific energy level, which is what I said when we were talking about the orbits. That there aren't any electrons between the orbits. If you remember, we drew it like satellites around, or moons around a planet. That's actually called the planetary model. And each of those levels is an energy level, and electrons do not hang out between energy levels. So when you look at the various models that have been proposed, on the left here is the original Greek model, in which the atom was considered indivisible and a hard sphere. In the middle is what's known as the plum pudding model, which was proposed by Dr. Thomson in the 1800s. And what it said is that the matrix, or the red part here, is the positive charge, and that the electrons were embedded in the matrix like little islands within the matrix. Now, the reason that this was called plum pudding model is because this looks like plum pudding that's made in England, where the electrons represent the pieces of plum and the rest is the rest of the dessert. Rutherford proposed a model that looks something like this, where the electrons were just a fog of electrons around a central nucleus. Now, this would not be consistent with discrete quantized electron distribution. But now here is the Bohr model. It's also called the planetary model, where you have the nucleus in the middle, and all the electrons are at the same energy level outside the nucleus. And you do not find electrons inside that circle or outside that circle. And as I said before, each circle of electrons represents an energy level, and as we labeled them before, it was K, L, M, N. It can also be labeled N equals 1, N equals 2, and N equals 3. And with each step out, it's an increase in energy. So an electron drops from level 2 to level 1, which is shown here, the energy that it loses is emitted in the form of a light ray or a photon. Now, the wave mechanical model describes electrons as waves instead of particles. Now, I don't want you to get too bound up about that. That's not really important, except to know that that's the definition of that model. The Heisenberg uncertainty principle is a principle relative to electrons that states that the position and velocity of an electron cannot be simultaneously measured with certainty. Now, what that means is that you cannot know where an electron is and how fast it is moving at the same time. You can know where it is, and you can know how fast it's moving, one or the other, but you cannot know both. And this uncertainty is a very important part of the electron modeling system. Now, we showed in the previous slide electrons sort of dancing around the outside of the nucleus like a moon around a planet. And it's not really exactly like that. What's probably more precise is this electron cloud, which is, rather than a precise location for the electron, you have to talk about an area where the electron might be hanging out. And that incorporates this uncertainty principle that Heisenberg described. And these areas where electrons might be hanging out are called orbitals. So this first diagram shows the wave model and how the electrons travel as a wave with a certain radius to the wave function. And this is the cloud, and what you can see here is in the middle is the nucleus, and we're looking at the diagram on the right now. And right outside the nucleus is the first level of electrons, and you can see that there are 4 darker areas where the electron might be. Now, this doesn't represent a bunch of electrons hanging out there. This represents an area where the electron might be. And then farther out, you have, again, areas of probability where the electrons might be. And this is the electron cloud model, and it incorporates the idea that you cannot actually know with precision where an electron is at any particular time. Now, the orbitals, as you move out from the center, have different shapes. The internal orbit, the middle, or the one that's closest to the nucleus, has a spherical shape that's shown on the left here. As you move out, the orbits begin to develop different shapes, and these different shapes are shown here. That the second group of orbits that occur go along the various three-dimensional axes. You have the x-axis, the y-axis, and what's shown here is the z-axis. And then after that, geometrically, it becomes much more complicated. Again, you don't need to know this with any particular detail except that this occurs like this. So, in order to describe where an electron might be, they have what's known as quantum numbers. And the quantum number should be thought of as an address. So, for example, I live at 291 Rosemont Garden. Okay, that Lexington, Kentucky. So the address starts out in the United States. So the address starts out the United States. Think of this first number, n, like the United States. That's the principal quantum number, and it's the number that represents the major energy level. Then I also live in Kentucky, so that's L, okay? Or let's make L Lexington, Kentucky. And then so that's the angular quantum number. That's the second number. The third is M. That's my address, 291 Rosemont Garden. And then in the case of electrons, only 2 electrons can live in any particular address. And so they're distinguished from each other by the S quantum number, or the spin quantum number. So if we look at this, again, N is the principal quantum number, and it also tells you the shape the distance that the electron has from the nucleus. The second quantum number, also known as the angular quantum number, tells you the shape of the orbit. The third tells you the orientation in space, and the last is the spin quantum number. Now, unlike our house where we have 4 people live there, no 2 electrons can have the same 4 quantum numbers. No 2 electrons can have the same 4 numbers for their address. You actually have to think of this last part like a townhouse where one person lives on one side and one person lives on the other side, A and B. And so that principle is called the Pauli exclusion principle. That is the fact that 2 electrons have to have a different address. So what you have here is, if you start with the top left, this represents, let's say this represents hydrogen, which has 1 proton in the nucleus and 1 electron on the outside. It has a particular quantum address for its electron. N equals 1, L equals 0, M equals 0, S equals plus 1/2. The next element is helium. It has 2 protons in the nucleus, 2 electrons on the outside, and those 2 have the same address for N, L, and M, but that other electron lives on the other side of the townhouse. It has a spin of minus 1/2. So one electron has S equals plus 1/2, the other has a spin equals minus 1/2. So they have different addresses only in the fact that their spin numbers are different. Now when you move out to the next electron, because it's in level 2, and we're talking about lithium with 3 electrons and 3 protons, those first 2 electrons have the same addresses as the previous element, but this new one has N equals 2 now, L equals 0, M equals 0, and S is 1/2. And then the next one is the same except S is minus 1/2, and so forth. And we'll look at other examples in class about this. Now, we talk a lot about chemical reactions, but there are also something called nuclear reactions. And nuclear reactions occur when the change occurs in the nucleus as opposed to a change in the arrangement of elements. Something is called radioactive if it's unstable and produces a radioactive particle. Radioactive decay is the process where an atom changes in the nucleus and actually becomes another substance. So for example, uranium-238 goes through a series of nuclear changes and becomes another element, uranium-235. Or it can go on and become yet another element, a simpler element. The half-life of any radioactive element is the time it takes for 1/2 of the substance to undergo radioactive decay. Now when we talk about changes in the nucleus, we talk about types of decay. And when decay occurs, generally what happens is the energy is emitted, as shown in this diagram on the left, in the left lower corner, and some kind of particle is emitted. And depending on the type of particle emitted, you have the different kinds of decay. Alpha decay occurs when the nucleus changes such that it releases an alpha particle. And an alpha particle has 2 protons and 2 neutrons. So this is an example of that. This nucleus has undergone alpha decay, and it spits out one particle that has 2 protons and 2 neutrons. Notice there are no electrons, just 2 protons and 2 neutrons. That's called alpha decay. Beta decay occurs when the nucleus changes such that there's a release of a beta particle, and a beta particle is simply an electron. And then gamma decay occurs when the nucleus changes, and the only thing that happens is energy is released. There's no actual particle that comes out. So here's a diagram that sort of reviews all three of these types of decay. The first, on the left here, you see the electron being emitted. That's called a beta particle, so that's beta decay. Down at the bottom on the left, you see a gamma ray, which is a type of electromagnetic radiation, and it's just a waveform. It's not actually a particle. And then on the right upper part, you see the release of a alpha particle, which is an alpha decay. Nuclear fission occurs when a nucleus breaks apart. A nuclear reaction where the nucleus splits to form two smaller particles is called nuclear fission. A chain reaction is a reaction that occurs in which there's a domino effect. That is, one reaction occurs, it releases a particle that hits another atom, causes it to release a particle, which hits another atom and causes it to release another particle, and in a domino effect until all the atoms have reacted. The critical mass is defined as the minimum amount of material that's required to support a chain reaction. And breeder reactors are atomic reactors that produce more atomic fuel than they use. And the way they do this is the particles that they emit from one type of fuel produce a new type of fuel, and they actually produce more fuel than they consume. So here's an example of a fission reaction. Uranium-235 is struck by a neutron, which splits it apart into barium and chromium with the release of 3 neutrons. Now notice, obviously, those 3 neutrons could hit another uranium, and you could have what is known as a chain reaction. So this is an example of the chain that can occur. You have the first that's struck by a neutron producing the 2 chromium and barium, releasing 3 neutrons that strike 3 more uranium atoms, and so forth.